in the near future.
It better be soon because we only have 2 weeks.
Well, notice I didn't say what day or even today, because I don't want to narrow myself that much. So, yeah, it's probably a busy time of year for everyone.
Do you know when our final is?
I believe I put it on the syllabus. Do you know whether it's Monday or
Monday.
Wednesday?
It's Monday? Okay. Thank
So it'll be
God.
Monday at 8:30. I think it's Monday.
I have 2 on Monday and 2 on Thursday.
I have Monday, Wednesday, Thursday, so it's yeah.
I think so.
Actually, I guess the one of them on Wednesday is all
Okay.
it's not a real final, it's just
Oh,
watching
really?
speeches.
You're in the speech class and that's all your final is?
No, it's
Oh.
human growth and development.
Ah.
We all get a final section instead of a test. Mine's on Wednesday. Mine's tomorrow.
Okay, so last time we started introducing the idea of a gas inside of a cylinder with a piston at one end. Everything's insulated, except at the very end of the class. And we said that, okay, suppose that this gas expanded and changed the volume of the gas by delta V, and then the work done by the gas would be equal to P delta V. And then we said, well, that's the only thing that the gas does that happens to the gas. You know, this had to be equal to whatever the change in energy of the gas is. Because there's 2 ways for energy to change, either heat flow or work done. And so the change in energy is equal to the heat flowing into a system minus the work done by the system. This could also, you could also include heat being generated or something by some, putting things, reactants or something inside of it, and then just be the system.
That doesn't make sense. Like it makes sense. Wouldn't it make sense? I guess it's the same thing. Like
Yeah.
the heat that's lost
on what you
being
call the system.
subtracted off of it.
Yeah, this would be negative if heat were being lost.
Oh.
Positive if heat were being added to the system. And then we said, well, if this were insulated, get rid of this cube, and we did everything with that work. Now there is an issue with this. Does that really make sense? So, let's say I had a piston like this with gas in here. Let's get it raised up. Would this, if I'm raising it up slowly, do you think that the pressure in here would keep the same? Oh. So actually, this particular situation would never ever happen in reality. What's that?
That's what I could text you yesterday. Like with
Oh,
the
that's what you
pressure.
were asking?
Yeah, because I thought the pressure like changes when it goes up and stuff.
Yes, we were basically saying this pressure is constant,
Oh,
the outside
okay.
pressure, and then the amount of work done would be this if you increase the volume.
Okay.
So basically what we were doing is we were forcing the volume to increase without changing anything else. And that's probably not a very realistic situation. So today what we're going to do is we're going to try to adjust things a little bit so to make it a little bit more realistic and to understand how pressure inside gases changes with volume and temperature. And just to be specific, if you guys had, most people probably had some sort of chemistry, right? Probably everyone's seen the ideal gas law. What's that?
Kidner.
Yeah, well, Kibner in chemistry.
Oh.
Yeah, but yeah. So, As this thing expanded, it turns out the pressure in here would have to be going down. Or, you know, at the same time, or or the temperature decreasing, but then that would make the pressure go down. So there's all sorts of issues with the situation we had set up last time. Okay. They'll do both, yeah. In reality, it's really hard to figure out what it'll do. So we'll have to kind of be a little bit careful. One thing I would like to do is I'd like to change this equation around somewhat and say that the heat that flows into the system could be equal to the change in energy of the system plus the work done by the system. Okay, and this is probably this is another expression of this, which is just basically saying that energy is conserved. And so we might be using this a little bit. All right, let's look at the gas inside of here. So it's experimentally found that if you have a piston, or if you have a cylinder with gas, or it doesn't have to be a cylinder, if you have a volume of the gas and you put pressure on it, if I plotted pressure as a function of volume and kept the temperature constant, what you would find is that the pressure goes like 1 over the volume. Okay? So it's proportional to, you can say that's equal to some constant over the volume. So as volume increases, pressure would go down. It was if I were to plot temperature as a function of volume and keep the pressure constant, it's found that as I increase the volume, what's that?
Temperature increase.
The temperature, what was it?
Temperature increases as volume is increased.
Well, yeah. Well, that's what we were assuming there because it did work. So this is a little bit confusing.
Okay, you keep the pressure constant. How are you changing your volume without changing your pressure?
You can't, that's the situation. But let's say that, I mean, you probably, okay, you probably can. But other things have to be changing.
Temperature.
Okay? So on this one, well maybe, okay, let's see if we can, okay, you just threw me for a loop.
Sorry, I'll go home.
No, that's okay. It's okay,
That
yeah.
doesn't make sense though.
Let me just think about that for a second. Well, how would you actually do that? Good question. All right, so if I'm changing temperature and changing volume, oh, what I would be doing is I would have, say I have an external pressure, and I just heat up the system. Okay, what would happen?
Then
So let's say I have a gas, and this isn't insulated or anything. See, the situation we had before is this was an insulated cylinder. Now let's say that I put a fire underneath it, right? And so I heated up the gas. What would happen?
It would want to increase the volume.
yeah.
Yeah.
Keeping a pressure on it to keep it from increasing is what you're saying, correct?
Yeah, so if I'm keeping it at I'd have to increase the pressure. If I were, let me do temperature on this axis and volume on this axis, okay? So if I'm heating up the system, increasing the temperature, keeping the pressure constant, you would find experimentally that the cylinder goes, that the piston goes up, right?
Yeah.
Yeah.
It actually goes up linearly with the temperature.
So the pressure does increase or it doesn't?
So the pressure's constant because the
Pressure
thing
equals
is moving
constant.
up.
The pressure from the outside is
Oh, 'cause that.
So the pressure in this situation is P atmosphere, okay? Or whatever it is.
But the piston would move up, wouldn't it?
The piston would move up if I started heating up the gas.
the pressure on the
Yeah.
inside
Yeah,
would
yeah.
increase
Yeah, it
to
would
like
increase.
overcome the pressure on the outside. to
Well,
increase the
no,
volume.
No, the pressure on the inside
If
would
this
stay
thing
the
is,
same.
the
Why?
pressure,
Because
if this
it's,
piston's free to move,
yeah, the piston's free to move.
if
so
it's
the
sitting
pressure's
there,
staying the same.
then this also has to be the same pressure P atmosphere here, so that the forces on the piston, the force downwards equals force upwards. Or maybe it'd be easier to look at it sideways so you don't worry about
But
gravity.
what about as it's moving?
As it's moving, as long as it's moving slow enough that we can assume it's not accelerating this piston, then, yes, there's no net force. This would be P atmosphere. Make sense?
But when it goes from 0 to, was when I was talking about, when it stopped and then it moves. Like,
Oh, you mean that, no, there's probably, yeah,
that's what I was talking about.
but I think that would be infinitesimally different from that. Yeah. Okay. But does that make sense? If I start heating something up, the volume should increase. It's also found experimentally that if I kept the volume constant and then heated it up, that the pressure would be increasing. Make sense? And you've probably done that. That makes sense. And then finally, it's seen that if I take if I start pumping more air into here at a given pressure, so the amount of air, I'm going to call this N as the number of air molecules. If I started looking at the pressure as I pumped and kept the volume constant, the pressure would be increasing. And if I wanted to do the same thing with the volume here, and keep the pressure constant, it would also be increasing. So I could do P or V, and then V or P is constant. Okay? And it would both look like that way. And so people did these experiments with a bunch of different gases, and then they combined everything into one single formula that would describe all of this. This is called the equation of state for an ideal gas. What they found was that P times V is equal to N T times a constant. Let me put that constant there, K. This is the ideal gas. This is ideal gas law. Okay.
Is like N still the number of moles of gas?
No, N is number, let me just, you've probably seen before, I'm guessing. You've probably seen the expression PV equals nRT, where this is the number of moles, this is the, and then R is the gas constant. This thing's very, very similar. Let me just indicate what this is. This is the number of molecules and then this is called Boltzmann's constant. So this will be our, shoot, it's like our third different K. in this class. So don't confuse that with wave number or spring constant. Boltzmann constant. Boltzmann constant. Okay. And the numerical value for K is 1.38 times 10 to the minus 23. Well, I think it, yeah. Times 10 to the minus 23. And then the units would be pascals, meters cubed over degrees C or Kelvin. Okay. Okay, so that's the relation between all the different pressure, volume, number of molecules, and temperature inside of the gas. It's all summarized in that ideal gas law. And of course, this makes a situation inside a closed piston a lot more difficult if I try to do work and stuff, because I have to change something. More than just, I have to start, you know, if I want a constant pressure, I'm probably going to have to let heat flow in, that type of thing. Let's go ahead and do some examples. So you probably have worked with that before. Just guessing, but we can do some quick examples. Let's say I have a container of gas where the volume can't change. And let's say that it's 1 atmosphere initially at temperature equals 300 Kelvin. Suppose and this is let's say that there's about 10 to the 23 molecules in it. Suppose that the temperature raised to 500 Kelvin. What would be the final what would be the final pressure? That makes sense? Just give that a try, make sure you can get all that stuff.
Sometimes I don't, it's right. Well, 'cause that's
It's okay. Just the unit or the distance, the size of the temperature is the same. Kelvin. That's right. So this agrees 200, 200 Celsius. Got it.
I got an answer.
Got the answer?
My way of thinking, none of this matters. You know, you want that much for it. I'm telling you, you got to take it down. You're gonna have to do something. None of this matters. Now,
It's 418. No, that's 500 divided by 2. Should be. All right, what do you guys get?
1.6782.
atmospheres.
Okay. I probably should have used this SI units, shouldn't I? To not be confusing. But it's okay. So 1 atmosphere, by the way, is 1.01 times 10 to the 5th pascals. But we can worry about that in a little bit. Everyone done? You good? Okay. So if we know, well, I mean, you could do P. Let's just do this very carefully. PV equals NKT. Okay, we don't know what the volume is. We don't know what N is. So I can do P is NK over VT. Okay? This is a constant for this situation. You know, that's not changing with this situation, since volume's the same. And I would just call that maybe A. It doesn't really matter. Okay? So we have P is constant times T. Okay, now if we, 1 atmosphere is equal to that constant at 300 Kelvin. And so the pressure final is going to be that constant times 500 Kelvin, which is the final temperature, right? So I could these are what we know. So I could solve for A in this situation. I could say that A is equal to 1 atmosphere, and I'm not adjusting it to pascals right now, just easier not to, over 300 Kelvin. Take that, plug it into here. And you would get that the P final is 1 atmosphere over 300 Kelvin times 500 Kelvin. That 500 Kelvin divided by 300 Kelvin, that's just 5/3, right? So this is 5/3 atmosphere, which is 1.67 atmosphere roughly. And then you can plug that into here and get about 1.67 times 10 to the 5th pascals. Okay, makes sense? 1.68, yeah. You know, one of the things is that it's you don't have to worry too much about, you know, if you have one thing that's varying, put everything else into that constant. You want to do another? Okay, let's do another. let's say I have the same situation where this is initially at T initial is equal to 1 atmosphere. When N is 10 to the 23rd, and N's just a number. And we have some volume here. Now let's suppose that we pump molecules into here. Okay? So N initial is that. So let's say N final is 3 times 10 to the 23rd. So what is final pressure? Well, this whole thing is just held at some temperature T. Should be pretty easy, right?
I hope so.
What about the?
We don't have volume?
No, you don't have the volume.
We don't care. You're not trying to.
Think about it, good. Yeah? Now show it mathematically. Now show it mathematically. Simple. Did everyone get it? it's pretty clear that, since the, I plotted it up there earlier, that, it's just a straight line. But if I just plotted pressure as a function of the number of molecules and keeping everything else constant. So it's pretty clear if I triple the number of molecules, I'll triple the pressure, right? So you should get 3. Let's make sure that we get that when we work with equations, okay? And because that part, for more complicated problems, being able to work with the equations is helpful. So let's do the PV equals NKT. T. Now we're keeping T and V constant here. So I could say P is equal to N times KT over V. I'm just going to call this a constant, okay? I'll call this and A, constant. So initially, I know that I have 1 atmosphere here is equal to N is equal to 10 to the 23rd A. Okay, so A, solving for that, is divide both sides by 10 to the 23rd. It'd be 10 to the minus 23 atmospheres per molecule, or per number of molecule. Okay. Now that's what this constant is, and so now I can just plug in what I have, what P will be when I have 3 times 10 to the 23rd. So P is going to be final, will be 3 times 10 to the 23rd molecules times A, and then this is 10 to the minus 23, we saw. 23 atmosphere per molecule. When I multiply that out, I just get 3 atmospheres. Make sense?
You don't have to change it to Pascals.
Yeah, and I could change this to Pascals. That's 3.03 times 10 to the 5th.
Is that negative 23?
This is negative 10 to the 23, yes.
Okay. Oh yeah, you did it.
By the way, really quick, what's the, in terms of joules, what's the gas constant R? Does anyone remember?
0.8. If there's an 8, there's a 0, there's a 2.
Well, that's when you have
P and RT.
P in atmospheres and yeah. But if I have it in pascals and stuff,
Why is it,
in meters, yeah.
why is it 10 to the negative 23?
So I solved for what A is.
Yeah.
So 1 atmosphere is 10 to the 23rd
Yeah.
molecules times this constant.
Okay.
So I solve for that constant, I divide both sides by 10 to the 23rd, which is just 10 to the minus 23rd. Okay.
Okay.
Anyway, that's one way to do these problems. You can do things like take ratios, but try to work out what you're happy doing. Make sure you can put mathematical. Make sure you can do it with the equation, because a lot of things are pretty simple. You can just guess what the answer is, and you keep multiple things constant. But then when you start to let other things vary, it's kind of your intuition breaks down. Okay. Last time what we mentioned, we talked about heat capacity at constant pressure. And we were assuming, in this case, that everything was insulated and this is still moving. And we were writing heat capacity as a change in energy. Now that is actually sort of misleading, because that was a difficult situation to deal with. So I would like to be more precise with that today. And, oops, I erased it. That's why I wanted to start with this expression for the first law of thermodynamics. And that expression was that the change in energy would be equal to the heat flowing into the substance minus the work done by the substance. And I could rearrange this a little bit by adding work to both sides and have that Q is equal to the change in energy plus the work done. See where I got that? Okay, there's a reason it's called heat. This is heat flowing in. Write that right. Heat flowing into substance. And this is the energy, this is the change in energy of the substance, this is the work done by the substance. There's a reason why we call it heat capacity, because the usual definition actually just isn't just the proportionality between the change in energy and the temperature, it's actually the proportionality between the heat flow into the substance and the change in temperature. So if I just had something like this, make the walls no longer insulating so that heat can flow from the outside, or you can heat it up, then there's a relation between the amount of heat that I add and the temperature that increases. And this is the usual definition for heat flow, and I guess the one that we should use from now on. It's found that if I add, say, 5 joules of energy in heat, that amount of energy is equal to a constant times the temperature rise.
So the change.
Delta T. Okay? And so this will be what we're going to deal with. This is heat capacity. And in our example yesterday, where we didn't have any heat flow, we were just looking at the change in energy of the gas. It was sort of misleading to call that the heat capacity. I'm sorry about that. This is a real definition. Okay. The relation between the amount of heat I add to the system and then how much the temperature increases.
Does that work also equals to change in T?
That was what we were doing it last time, assuming that there was no Q. We were just changing the energy of the substance by doing work on it. That is true, what we were doing, assuming everything we assumed, that I could change the volume without changing temperature or pressure, which just isn't, that's not a realistic situation. And so, in this case, we're going to add energy to it. Just see, in a real situation, how much the temperature changes. It'd be nice to be able to derive what C is from the ideal gas law. We can end up doing it, finding out what the work is from the ideal gas law. But actually, it's difficult to derive C from just that. I'll give you some expressions for an ideal gas. If the gas is monatomic, you know what monatomic means? Molecules are made out of one atom. Well, there's two different types of C's, actually. That are tabulated. There's what we call CV. This is heat capacity at constant volume. That's if I add heat but don't let the volume expand. That turns out to be 3/2 number of molecules, KT. If I allow that piston to expand, as it's expanding, the gas is doing work, and I'm pumping heat into it, and it's doing work with some work with that heat. I have to pump in more heat to get the same temperature rise. And so there's a second one called the heat capacity at constant pressure. At constant pressure. And that turns out to be 5/2 NKT. Let's relate that to these things really quick. So we see that work done it's done only by expanding gases. If the gas remains at a constant volume, it doesn't expand at all. It doesn't do any work. So work is 0. Well, it's equal to P delta V. That's equal to 0 for constant volume. That's pretty straightforward because V, the change in volume, 0 for constant volume. I mean, it's like an identity. Now, so that means that Q is equal to just delta E at constant volume. Any heat I add just changes the energy of the gas. It doesn't let the gas, the internal energy of the gas doesn't let the gas, if the gas isn't doing any work. And we find that in this, and then in this case, this would be 3/2 NKT, delta T, change in temperature, delta T. Now, we can, from the ideal gas law, which is CV delta T. From the ideal gas law, we can get what the work is done when we allow the pressure to change, or when we allow the volume to change at constant pressure. So from ideal, and then we'll be able to see how the difference between the CP and the CV is. From ideal gas law, we can see that PV equals NKT. So if I allow the volume to change, N stays the same, pressure stays the same, I could say that PV final is equal to NKT final. PV initial is equal to NKT initial. Subtract these two. Subtract the initial from the final. And I could say P times V final minus V initial is equal to NKT final minus T initial. Or P delta V is is equal to NK delta T. This was the amount of work done by the gas. And so I could see that at constant pressure, where I allow this thing to do work, I could take this and put this into here. That's good for an ideal gas. And I would see that if this is delta E, then at constant pressure, Q is 3/2 NK delta T, that's the delta E, plus NK delta T. And that's 5/2 NK delta T.
Oh, are you like continuing with the
Oh.
plus delta T?
Yeah, I'm probably not
I'm
doing
just
good.
making sure.
Okay, so I took this Q, which was the change in, the amount of heat added is the change in internal energy plus the work done by the gas. The work done by the gas using ideal gas law, we can actually calculate as long as the pressure is constant. And so I plug that into here. This is all at constant pressure, by the way, allowing work to be done.
What is that? After the K delta what?
Yeah,
The bottom.
Between delta T and
This one?
Yeah. Oh, delta.
the one above it there, and in the middle.
Let me, all right.
I
So
know
this
that.
change in internal energy when I add a heat is 3/2 NKT. So Q is 3/2 NK delta T. That's the delta E plus NK delta T. Okay?
How do we know that delta E equals 3/2?
That's something we didn't, we had to just give.
Okay.
So, this thing comes from what's called kinetic theory. You can get it that way. But this is something that is beyond, we're just given that. There's a heat capacity at constant volume, which is basically the change in internal energy when I add a heat, is 3/2 NK delta T. All right, let's do some examples, okay? And then when I add, and then I allow it to do work, I see that Q is actually 5/2 NK delta T. And so you can see that, for heat capacity, it should be just 3/2 NK. And so you can see that this thing here is the heat capacity at the constant pressure. And if I knew the one at constant volume, I can get the one at constant pressure using ideal gas law. That's all I wanted to indicate. So these two things are related. And it's not a mystery where, it's a mystery where you get this, it's not a mystery how you get this once you have that. Let's do some examples.